Stuart here. Today we're going to talk about an advanced queue pattern called pacing and overrun. Before we get started though, it's important to know that enterprise queues have properties that simpler queuing systems don't have. There are too many of those to discuss here, but they include things like HADR, massive scalability. But for the purposes of this pattern, there are three key things about enterprise queues we want to take advantage of. The first is that you can enqueue messages for the future. So for example, if you have, as we will have in this case, a message that comes along and lands in a unit of work, and that unit of work, for whatever reason, can't process the message right now, it can put the message back on the queue to be dequeued a while later. And so you can use things like exponential delay or retry for things that are transitive, or maybe the backing systems are too busy. And so that allows you to have very robust units of work. The second is that message metadata is mutable. So every time you process the message, you can update its metadata. You can update something like the message version, the last retry timestamps, retries, type of message, and whatever. And that's very useful in building these systems because that's a place that you can put state that goes along with the message without having to extend the message's schema. And lastly, and most importantly, and it's so important we have a whole other video on message leasing, that leasing is a key component of having units of work that will always successfully be processed until the message itself expires. And in enterprise systems, typically you can give message lifetimes on the order of days or weeks. And so if that's unlikely and we have a good unit of work pattern, and I'll show you that later, you can use leasing to make sure that you don't lose units of work. So the sort of corollary that goes with that, those three things are, you have to make sure that your unit of work can reprocess essentially the same message over and over and over again without doing any harm. So you need to be able to keep track of, in your database where the operations are taking place or whatever, that in fact the unit of work may not need to execute because it's already done that unit of work, and we can just tell the queuing system that this message is successful and it'll go away and we can go on to our next thing. The other thing we need to do is we need to be conscious about messages going to dead letter. Badly implemented queuing systems, messages show up in dead letter for reasons other than code explicitly putting them there. And each of those represents a lost unit of work. Whereas if I go and I grab a message and it's malformed, or it doesn't pass some other validation, for example, it wants us to update record number 45, and there is no record 45, that message is bad. I can annotate the metadata on that message to explain my complaints, and then I can explicitly send it to dead letter, where a secondary process, a monitor or some other operational procedure, will alert the operators that we have something unusual, a dead letter. Dead letters should be incredibly rare. I have done message processing systems that process as many as 2 to 3 million messages an hour, and the number of dead messages we get in a week is in the single digits typically. So if you find that you have a lot of dead letters, something is badly leaking about your unit of work pattern. And you didn't implement leasing, you didn't implement it correctly, or you took the wrong action for a particular error or problem. And really, there's only three outcomes to a unit of work. The message is bad, it needs to go to dead letter. The message is good and we were able to completely process it, in which case it can be DQ'd, it can be marked as done. Or the message couldn't be processed successfully and should be requeued. And here you can leverage the time delay to sort of give yourself some runway to have whatever dependent system wasn't ready again. And then if your unit of work completely locks up, it vapor locks, or it just stops, it goes off in a la-la land, adding leasing puts the safeguard back that unless you act, knack, or dead letter that message explicitly in code, that it'll go back on the queue to have someone else process it. So those are important sort of fundamental properties that enable this pattern. So let's talk about the pattern itself. Got a unit of work behind a queue. The unit of work can connect to many data instances based on an identifier. So it might be tenants in a tenanted system. It might be different kinds of work. It could be, for example, order routing. These orders are drop ships. They go off to the vendor. These things go off to the Phoenix warehouse. Those things go off, right? Whatever your thing is. So we have both a unique identifier that we're using, but we also have a component graph of subparts. And the other thing that's typically part of this is there's typically more than one message producer. So some business process over there does something that impacts the state of something else. Usually in domain-driven design, we use queues to bridge between domains, sometimes facaded by a service to provide anti-corruption. And you can go watch our domain-driven design series to learn about that. But the point is, you can have lots of different things that are telling you that, we need to have one of our units of work do some work for us. And those can come from all over. So we're assuming in this example that there's more than one producer. We want to make sure that the equivalent message is not reprocessed. That's called overrun protection. If your code is truly reentrant, you have sort of first level overrun protection, because after the message is validated, and the bad message would stop processing and be thrown to dead letter, right? But after the message is processed, there's some other way of looking up and asking an existential question, which is, have we done this unit of work for this part of the subgraph or this ID, yay or nay? And if it's something that's periodic, like updating a search index or whatever, have we done it sufficiently recently that doing it over again would be, an expensive waste? So that's overrun protection. And combined with overrun protection, that is the ability to detect whether or not we're working on something right now that we have a message for, or that it's already been processed. The third thing is, well, it's been processed, but in the time window. And that process of delaying the processing to do the update later so as to optimize the number of times an expensive unit of work runs against a particular subgraph for an ID, or a set of IDs is even more typical. We implement pacing, and pacing is just delaying the message delivery and incrementing the retry count, because obviously what we don't want is the Flying Dutchman messages that just get booted into infinity. And we have an assumption that after some retry threshold, in either time or retries or both, that if we haven't processed this exact message, we process something that looks like it. And so we can safely mark that message as being processed. And that requires a little bit of thought and testing, but again, with observability, you should be able to figure that out and tune it, be very conservative to start with, and sort of become more and more strict in terms of time windows and durations and stuff based on, how current the data has to be and how long the downstream process takes. For example, if you're building or rebuilding an e-commerce product search index, that could take a really long time, and you don't want to overrun it. And if you've just finished it and you get the message to do it again, you probably don't want to start that right away. So pacing overrun systems have built into them this concept of eventual consistency, right? That we don't have to necessarily do it in the moment. And parenthetically, in most business scenarios, doing it in the moment is not actually a requirement. Your business may think it's a requirement, but it in reality is not. All data systems that are not doing data processing in near real time, which is breathtakingly expensive, have eventual consistency baked into them. And if the data is then scattered across, multiple data sets and secondary things like caches and indexes and, BI and reporting objects, right? You don't have internal semantic consistency in real time. You have eventual consistency, which is why for all those systems, there's a piece of metadata called as of. So that when I'm getting data and I'm looking at it as an end user, I can say, this is how it was 30 minutes ago. And when it gets updated, I'll be able to tell that too. And in fact, if you have a good pacing and overrun system, you can supply your end users with a button that I guarantee you, will click on, like a hamster clicking the reward button for a food pellet that says, recompute this thing. So, here is the architecture for a pacing overrun system. It's based on an enterprise queue, so leasing and all the other things we talked about are baked into the queue. We just assume that they're there. So the messages are dequeued by a unit of work dispatcher. In Azure, it's typically a function. And then it decides, it has to make all the decisions about whether or not to pass that message on to the unit of work for processing, or kick it back to the queue, or mark it as done. And the way that it can do that is to leverage a state cache, which in this example I have as Redis, which is what I normally use. And both the units of work and the dispatcher can read and write the cache, and the dispatcher can use the state of the cache from the last successful processing of a particular unit of work to know what it should do dispositionally with the message it just got, which we'll look at in a minute. And then it's an enterprise system, so we want logs and diagnostics and observability. And for the work that we do in Azure, we typically use App Insights, but every platform will have something. Because you want to be able to go look at it and sort of see what's going on. And you also want to know if any of the units of work are having higher than expected failure rates, or because the things they're connecting to on the back end don't have enough throughput or whatever. So, not too many moving parts here. The units of work can be in the same binary as the dispatcher, or they can be, in their own scale set. And in something like C#, they can just be a task of T, right? And we're spinning up new tasks for new units of work and up to some level. And so you can use a task pool or something like that. And they're pretty easy to implement. Our friend, the cancellation token, is a big deal here, as is not returning void from units of work. Units of work should return task of some result object. And you should do something with it. Okay. So that being the case, here's kind of the basic flow of a paced system that has overrun protection. So everything but the can process box, right, is the traditional leasing flow. And the can process box is what makes the decision that the message, the previous step says, yes, the message is valid. If it wasn't, we ended the process and dead lettered the message. So are we about to overrun this unit of work? Is the unit of work already processing this particular type for this key range or whatever? Or has it processed it so recently that we don't want to immediately reprocess it? And that is the pacing overrun protection, is that can process box. And notice it's a binary, right? If it's no, we're going to put the message back on the queue with a delay. If it's yes, we're going to go ahead and dispatch a unit of work. And the unit of work can end in 3 outcomes, right? It can either have a recoverable error. So, we needed to open a connection to the SQL server in our unit of work. The SQL server says, hey, I'm not here, I'm busy, I timed out, whatever. That's a recoverable error, right? It's resiliency. So we have some built-in resiliency in our unit of work that works in the domain of milliseconds to at most a second or two. When we need to take a nap for longer, the trick is we're going to put that message back on the queue, and we're going to, for each retry, we're going to do it to 2 to the n minutes, where n is the number of retries, and you can have any formula you want, but typically you want something exponential, so 2 to the whatever is typical. The message can just not be processed, like the queue never hears back from your unit of work instance. And that's a timeout, right? And it's going to requeue the message, and it will eventually come around for processing. So that's your unit of work has jumped into outer space or had a critical error that was uncaught that didn't result in the recoverable error path, right? And then the last thing is it worked, right? We send the equivalent of an ACK to the queuing engine, and the ACK, marks that message as being completed, and eventually it'll fall off. You may ask, why doesn't it just delete the message from the queue right away? And the answer is, if your queue is actually a topic, not all of the consumers may have consumed it yet. So if you have messages that are consumed by different sets of units of work, you want an engine that doesn't delete the message. It just says this particular unit of work set has processed this message successfully, and that's metadata the enterprise queue keeps track of for you. So there you go. There's the overrun and pacing pattern. You can see a pacing pattern demo in my GitHub. You can see the leasing pattern in my GitHub as well. In that case, I'm using Rabbit because you can just spin it up as a container on your desktop and play with the example. I thank you for your kind attention.